support vectors are those points in both the classes which are very near to the hyperplane that you have chosen. So this is the hyperplane that I have chosen. Then I'll go and see which is the point which is nearest to either side. Hmm? If this is the point that is nearest, what will I do? I'll just suppose this is d distance. I'll just go to other side d distance and make this parallel line. Okay, so thus I get a margin. So this hyperplane that I have chosen, my main hyperplane, is equidistant from these margin hyperplanes. Okay, where do I draw these marginal hyperplanes? I just move from this plane to the classes, and the first point that I get, which is nearest, I just stop there. Or maybe I move on this side, I get the nearest point, I stop there, and equidistance on the other side, I make the line. So this point is at the center. Okay, so these are support vectors. So what are support vectors? The point closest to the separating hyperplane is what is a support vector. Not only do we want the instances to be on the right side of the hyperplane, but also we want them some distances away. एक तो ये है कि न सिर्फ हम ये चाहते हैं कि ये जो पॉइंट्स हैं, हाँ, ये जो पॉइंट्स हैं बराबर से इस लाइन की उस तरफ ही होने चाहिए. अगर ये बी क्लास में है और ये ए क्लास है, तो डेफिनेटली ये ग्रीन वाला पॉइंट इधर तो नहीं होना चाहिए, ये भी हम चाहते हैं. मोरोवर वी वांट दैट दीज पॉइंट शुड बी एज फार एज पॉसिबल फ्रॉम दिस हाइपरप्लेन. ये जो हाइपरप्लेन है उससे सबसे जितनी ज्यादा दूरी पर हो उतना ही अच्छा, उतना ही बेटर क्लासिफायर होगा हमारा. इसीलिए नाउ वी हैव गॉट दीज टू ऑप्शंस हियर. In fact, you have many options. You have to look at the best option. So if you have these two options, which one are you going to choose? In this case, what happened, this line, we just moved on the other side and we saw, okay, this is the nearest point. So what we did, we moved the same distance on the other side and we made this line. Okay. And in this case, we moved on this side and we saw that this is the nearest plane. Okay, fine. Then we just moved the same distance on the other side and we made this line, because this line, the center, the dashed line has to be in the center. Now what we see is, now this is what in red is the margin width. Now what are we going to look at is the maximum width, because that is would be the best classifier, so that we'll not have any other points which are misclassified. Also there, which happens to put it in everything in one place. This the line that is separating is the hyperplane. There are margins. These are the lines which are going to pass through the nearest point, and these nearest points are what they are called support vectors. So hyperplane splits the data because it is as far as possible from these support vectors, which is another way of saying we maximize the margin. So what are we looking at? We are looking at maximizing the margins. Okay. Not only do we want the instances to be on the right side of the hyperplane, but we also want them some distance away. That's why we are looking at big margins, isn't it? The distance from the hyperplane to the instance closest to its margin on the either side is called the margin, which we want to maximize for the best generalization. Now that we know that we are trying to maximize the distance, तो हम क्या करना चाहते हैं, वो जो margin है, वो मैक्सिमम मार्जिन वाला जो हाइपरप्लेन है उसको चूज करना चाहते हैं. वी आर ट्राइंग टू मैक्सिमाइज दैट डिस्टेंस फ्रॉम द सेपरेटिंग लाइंस टू द सपोर्ट वेक्टर. Okay, the separating line matlab the hyperplane, the main hyperplane. Okay, the separating line to the support vectors, we need to find a way to optimize this problem. So how do we optimize this problem of the maximum distance? So we have to find the maximum margins. So this line can be represented in this ways. Okay, so when we look at this figure 6.3, that is from Peter Harrington's book, our separating hyperplane is of this form. So omega xi, you can write it any ways. Omega vector x vector plus v. So we want to find a distance from A. So what do? Every point that is there, we are going to pick that point and find the distance from that point to this particular line. व्हाट विल गेट दैट, ओके ये जो पॉइंट है वो सबसे पास में है इसके, है ना, तो हमारा हाइपर प्लेन क्या होगा, इधर से इतना ही पतला ये हाइपर प्लेन बनेगा, ये ना कि ये इतना बड़ा हाइपर, इधर इधर जाएंगे तो ये दूर काफी दूर है, और इधर आएंगे तो ये सबसे पास में, ये सपोर्ट वेक्टर हो जाएगा हमारा। ठीक है, सो वी वांट टू फाइंड द डिस्टेंस फ्रॉम ए, हम चाहते हैं ए से कोई हर पॉइंट से आप डिस्टेंस फाइंड करना चाहते हैं, तभी तो आपको पता चलेगा कौन सा पास में है। You are just wanting to know the distance from every point to this particular hyperplane, and that can be given by this formula. huh? That is the mod of the line, the equation divided by the norm. Okay, the constant b is just telling you the offset, जैसे कि होता है ना intercept होता है ना, offset बता रहा है b. Okay, all this w and b stuff describe the separating line or the hyperplane for our data. So what are we getting in an SVM is an input data. ये पॉइंट से आप कुछ इनपुट डेटा है x1 x2 x3, ये फीचर्स हैं, x1 क्या है, सभी फीचर्स, वेट, हाइट, एज, ऑल ऑफ इट, एंड x y1 y2 y3 क्या है, ये क्लासेस हैं, ये कौन से क्लास में उसको ए क्लास में प्लेस किया है कि बी क्लास में प्लेस किया, प्लस क्लास में प्लेस किया है कि माइनस क्लास में प्लेस किया है. सो x1 इज अ x1 vector is the first row maybe, all the features, and y1 is the output, is the class. So what is the objective here, हमारा objective क्या है, we want to learn slope क्या होगी इस line की, है ना, what would be the slope, what would be the intercept, isn't it, if it is just a linear line. Okay, so we would want to know the value of w and the value of b to maximize our margin. So what is the margin? The double of the smallest perpendicular distance from the training instance to the separating plane is called the margin of the separating hyperplane. So this we have already done. What is optimal separating hyperplane? The hyperplane with the maximum margin is called the maximum margin hyperplane or the optimal separating hyperplane. So we have already talked about it. Support vectors, the point that lie closest to the optimal separating hyperplane is called a support vector. So how do you really find it? The mathematical formulation for this would be the SVM problem is of finding the equation of the SVM given a linearly separable two class data. So the idea is the data should be into two classes which can be linearly separable. Okay, so data set is given like this. X is represents the vector, Y represents the class label. So if we look at this, omega x plus b is equal to 0 is the best separating hyperplane. So this is what, ये जो पहला वाला जो equation है वो ये hyperplane है उसका equation है. And this less than 0, okay, is the equation for negative samples or B sample, whatever, B class. Positive sample matlab class A. So if this equation less than 0, if you get, this is for this particular line, and for greater than 0 is the equation for the positive samples, means the samples are on this particular line. So Y value, the class x y1 y2 and all of them are -1 एक particular class के लिए, +1 for a different class. This is how we are actually looking at it to solve the optimization problem. Okay, so जरूरी तो नहीं है कि कितना डिस्टेंस, जो भी कुछ भी डिस्टेंस हो सकता है ना, तो ये जरूर हमें मालूम है कि ये जो हाइपर प्लेन है उससे इस पर्टिकुलर हाइपर प्लेन जो सपोर्टिंग हाइपर प्लेन्स है डिस्टेंस क्या होगा, k डिस्टेंस. इफ इट इज k, दिस आल्सो विल बी k डिस्टेंस. Okay, so in general what you would write is what would be your this thing formula of the line would be omega x plus b is equal to 0, and for supporting lines it would be omega x plus b is equal to k, and for this one it would be omega x plus b is equal to minus k. And the width of this line can be given by 2k divided by norm. Now how did we get this? I'll just come to it in the next slides. The width of the margin can be got like this. How did we get this? We'll come to it. But what are we wanting to do is, now we want to maximize this width. This is what we are looking at. So what are we going to do is maximizing this is what is our problem. We are wanting to maximize this particular width, which is given by 2k by omega. Okay, but what we do is, to simplify, we make it ones. Okay, -1 and 1, और k को हमने 1 कर दिया ताकि हमारे mathematical computations become easier for us. Okay, so scaling w and b so that k is equal to 1. Suppose now we make k is equal to 1, and then when we solve it, what happens? This k would become 1. So now we are having a simpler expression out here. 2 divided by norm of w, and here also, instead of k over here, we get greater than equal to 1, less than equal to 1. Now this is actually easier to solve mathematically. That's thus we have just brought it to this level. Okay, so the explanation is given in this in the Peter Harrington's book. Why have you just reduced it 0 to 1 instead of -1 1? Because it is easy to compute. Hmm? So how do we really go and see the perpendicular distance? How do we get the perpendicular distance? हम क्या कर रहे थे, हर a point से उस particular line तक हमको देखना है कि distance क्या है ना. To find that, what we do is, the this expression of the line जो भी है हमारी expression of the line में, ये जो x है उसकी value place यहाँ करेंगे हम, divided by omega, norm of omega. This is how you get the distance from a particular line to that particular hyperplane. Now how did we get this? पिछली slides का ही मैंने यहाँ इधर रख दिया है. ये क्या है? ये particular चीज क्या है? This expression, equation of the hyperplane. So numerator में क्या है? Equation of the hyperplane, and denominator में क्या है? Norm of omega. Now if you want this distance between these points, हम ये hyperplane है हमारा, और ये जो soft hyperplanes है हमारे, the other hyperplanes हैं that touch the vector. These are the equations. ये वाली जो लाइन है उसका इक्वेशन ये है, ये इधर वाली जो लाइन है उसका इक्वेशन ये है हमारे पास. ठीक है, तो अब ये दोनों इक्वेशंस को अगर हमने लिया इधर, एंड वी जस्ट ब्रिंग दिस वन ऑन दिस साइड, सो व्हाट हैपेंस? दिस बिकम्स इक्वेशन 1, दिस बिकम्स इक्वल टू 0. 1 इधर चला गया तो -1 हो गया, इक्वल टू 0. दिस गोज ओवर हियर, इट बिकम्स +1 इक्वल टू 0. ओके, देन if you want to know the q distance, origin say I want to know this distance, isn't it? And I want to know the distance from origin to this point, then only I can know the distance between this point, isn't it? ये दो margin है, इसका क्या क्या है margin? तो ये d जो value है वो क्या है? q minus p. I'll get this d value. So let me understand what is q and what is p. So q is a distance from origin to my second line, isn't it? ये वाली जो line है. And p is the distance from the origin to my this line. So we are just going to apply this particular the earlier example that we saw. How do you get the distance? You write the equation up in the numerator, and in the denominator you write the norm. So distance कहाँ से पता करना है हमको? 0 0 से पता करना है ना, origin से पता करना है. तो आप क्या कर रहे हो? ये जो x की जगह पर आप क्या लिखेंगे? 0 0. When you write 0 0, what happens? This complete term vanishes off, and what you get? B minus 1 divided by omega norm. Similarly, for p, if I want to know the distance from the origin to this particular line, I'll use this particular equation, isn't it? This equation I have taken divided by the norm. Again, I am placing the origin 0 0 over here for x, and what do I get? This complete term gets vanished off, and I am left with b plus 1 omega. So now what I have to do to find the value of d? I have to just do q minus p to get it. So let's see whether I'll just go to the next slide to get it. So what did I do now? So what is the value of d? If you see here, the value of d, this d value is q minus p. ठीक है, तो q क्या वैल्यू क्या आ रहा है हमारा? b minus 1 omega divided by omega. q का वैल्यू क्या आ रहा है? b plus 1 divided by omega, right? So I've just placed it over here. What happens? B and b gets cancelled out. So what are we left with is 2 divided by the norm. So this is the distance between the two margins. Okay, two margins जो है हमारे उसका distance है. 2 divided by omega. And this is what you want to maximize, isn't it? We need to maximize the distance for the denominator. How will this get maximized? ये कब maximize होगा? जब ये denominator will be minimized, isn't it? ये पूरे expression को हमको maximize करना है, उसके लिए हमें denominator में जो भी होता है उसको minimize करना होता है ना. तो हम इसका मतलब क्या है? अगर हम इधर ले आए, अगर इसको हमें क्या करना है? Minimize करना है इसको ओमेगा को. Now, just because we know that omega is what this particular norm is a square root, isn't it? Square root hota hai, and to deal with this square root will become difficult. So what we do is we square it up. We just square it up for easy calculation, and we divide it by 0 because it becomes a quadratic expression up there. So to simplify it, we are just dividing it by 0. So this is an expression that you get, that you got to minimize to get an uh, optimal solution. Okay. So we can define the SPM problem as an optimization problem. Find a vector omega and the number b in such a way that this particular expression of ours is minimized. Now, what are we saying? Subject to yi. What is yi? Yi is the label of that class xi, and this is the expression of the class. Xi is each sample. I is any value 1 to n. The solution for this SVM problem is a classifier known as SVM classifier. So what is the idea? We are just going to minimize this particular expression of ours. So suppose we for a solution that you're finding, you got omega as omega star and b as b star. Okay. So let's see, suppose you got a SVM problem and then you found out omega star as one of your solutions, or a particular line मिली आपको और omega star you got, and b star you got. So what will you do is you will just assign it to this particular expression of yours. If it is greater than 0, then you say that the class label is +1. If it is less than 0, you say class label is -1. This is how you keep classifying the new data that has come in. Okay, and see, you may just want to see which is the best classifier. So this is what we do in SVM. Now, if we look at margins, there is something called a soft margin. Soft margin, hard margins. Hard margin जो अभी हमने देखे कि भाई अगर this is the particular clusters, these are the how your two classes look like. So what you will see is look at the support vector just near it over here. तो अब क्या करोगे, इसके just दूर पर आपने दूसरा वाला support vector line बनाई है आपने, और this would become your hyperplane. Okay, hyperplane will just, this is how it will classify. Now suppose if you just allowed this to come in, this point, if you just allowed it, what would happen? इतना बड़ा ये hyperplane हो सकता था, इतना width हो सकती थी आपके hyperplane की. So this is what is soft margin, wherein we are just allowing certain misclassification and penalizing such classification also. So we are allowing it. So there comes a slack variable. Slack variable allows this kind of a misclassification. So that what happens is, just because of some of the other points, only ये इतना पतला जो margin हो सकता था हमारा, उसको हमने इस तरह से बड़ा कर दिया. Because what is an optimization problem is to increase this margin, isn't it? We want to increase this margin. So soft margins of SVM help you do this. So this is a psi value which helps you do soft margin SVM. Okay. So in real life, what happens? Zyadatar you do not get different data very well differentiated, isn't it? In real life problems, two class data sets are not rarely linearly separable. There are two types of deviation. An instance may lie on the wrong side of the hyperplane and can be misclassified. An instance may be on the right side but may lie on the margin. कई बार रॉन्ग साइड पर क्लासिफाई हो सकता है, जैसे कि इस केस में, जैसे कि ये है पॉइंट, ये रॉन्ग साइड में क्लासिफाई हुआ है, और हो सकता है राइट साइड में क्लासिफाई हो मगर वो मार्जिन पर हो. ओके, So both these cases are taken care of with the psi variable, the slack variable called psi. So when it is on the margin, matlab, it is not sufficiently away from the hyperplane. कोई भी point on these margin, in this margin, means they are not sufficiently away from the hyperplane. So they do not have a lot of clarity. The classifier may not have a clarity. But we are just because of using slack variables, we are able to do this. Hmm. And you can see how it has really increased the width of from this to this, just because of soft margins. So in such cases, we introduce an additional variable psi, a slack variable, which stores deviation from the margin. So psi जो है उसकी value 0 होगी अगर जो point है that is correctly classified. For this particular point, the psi slack variable would be 0. For this particular point, the slack variable would be 0. And the slack variable would be anything between 0 to 1. अगर वो मार्जिन पर है, अगर करेक्टली क्लासिफाइड है, मगर ये वाला नहीं, जैसे कि अगर यही वाला पॉइंट होता इधर, ये वाला जो पॉइंट है इधर, वो इधर होता, करेक्टली क्लासिफाई हो रखा है मगर वो मार्जिन पर है, तो साई वैल्यू वुड हैव एनी वैल्यू फ्रॉम 0 to 1. एंड इफ इट इज मिसक्लासिफाइड, यानी ये जो ऑरेंज पॉइंट्स हैं, दे हैव दिस पॉइंट इज नाउ अकरिंग ओवर हियर, नाउ दिस इज मिसक्लासिफाइड, so what will happen, psi variable would become 1 for this particular point. इस particular point के लिए the slack variable will become greater than equal to 1. Okay, so this is how we, with the introduction of slack variable, we are able to do soft margins. Okay, so what happens now, our formula happens to what are we wanting to do, objective जो है हमारा न सिर्फ minimizing this particular expression of ours, but we are actually adding up all the slack variables, and we are also having a penalizing this thing, a feature multiplied to it. Okay, so this is what is C is actually called a soft error. And what is this? This is psi variable is the sum of all the slack variables out here. All the variables are have to be added. Slack variable, हर एक point के लिए slack variable निकालेंगे आप, उसको इधर add करेंगे. Note that that we are penalizing not only the misclassified points but also the ones in the margin for better generalization, though these latter would be correctly classified during the testing. C of the equation is the regularization parameter, or called the soft error, to fine tune your classification. Okay, it defines the trade off between the margin maximization and error minimization. If it is too large, means the C value. If it is too large, we have a high penalty on the non-separable points, and we may store many uh, support vectors and overfit. So the model that we have studied till now, that is the support vector machine, are generalized under the name kernel machines. Okay, what are kernel machines? Kernel machines are maximum margin methods that allow the model to be written as a sum of influences of subset of the training instances. Okay. See, kernel trick, there's a kernel trick. What is a kernel trick? It says that if the data is in a lower dimension, when we convert it into higher dimension, we are able to linearly separate. That is what is called a kernel trick. So यहाँ 2 डायमेंशनल में डेटा है, यहाँ इसको सेपरेट नहीं कर पा रहे हैं, कोई लाइन नहीं बना पा रहे हैं, ऐसे इस तरह की लाइन बन रही है. तो जैसे ही हम इसको फीचर्स हम 3 डायमेंशन में कन्वर्ट करते हैं, वी सी दैट these two classes become linearly separable. Similarly, if you are looking over here in 2 dimension, we are not able to look at it, right? तो इसको अगर 3 डायमेंशन में कन्वर्ट करते हैं, then we are seeing okay, these orange points are lying somewhere here down. अभी हम इसको एक प्लेन से सेपरेट कर सकते हैं. Okay, so this is what is called a kernel trick. So anything that is not able to be separatable in a lower dimension, we convert it into any dimension. तो यहाँ तो हम सिर्फ बात कर रहे हैं 2 डायमेंशन से 3 डायमेंशन. हो सकता है 2 डायमेंशन 10th dimension. We may go and look at various dimensions and see whether a particular is the data becoming linearly separable or not. Okay, so the kernel trick The kernel trick is to add a new input variable that is computed from the existing ones. So from the existing ones, you're just wanting a square of it or a cube of it. जैसे करके आप क्या कर सकते हैं, हो सकता है आपको एक इस तरह से सेपरेट करा हुआ डेटा मिल जाए, और फिर आप एक लाइन बना के या प्लेन बनाकर, मैनी प्लेन्स बना के उसे चेंज कर सकते हैं. The non-linear SVMs, you are converting, you're applying, getting a new function, you're applying it, and you're seeing that now my data is being linearly separated. In the appropriate transformation feature space, they are. So you have to find that appropriate transformed features space, isn't it? From 2 dimension, I've converted to 3 dimension. I've got this. Okay, now it is separable. Ho sakta it is not separable. So you will have to find the appropriate feature space wherein the data becomes linearly separable. Okay, most of the time it is possible. Okay, so original input attribute is mapped to a new set of input features via feature mapping, and since the algorithm can be written in terms of scalar product, we replace this particular as a function. Okay, as this. For certain functions, there is a simple operation on the two vectors on the lower dimension that can be used to compute the scalar product of the two images in the high dimension. So let the kernel do the work rather than do a scalar product. See, if you just do a scalar product, the computational computation is very high. But we are not doing a scalar product of the two features, but we are doing some kernelization, which will uh, not be heavy on computational cost. Okay. With this mapping, our discriminant function is known as this. They are saying we only use the dot product of the feature vectors in both the training set and test set. Kernel function is defined as a function that correspond to the dot product of the two feature vector in some expanded feature space. So this is how we represent it. Okay. Suppose कीजिए 2 dimensional features and two vectors are there. Now what are we doing is this x1 y x2 है, हम क्या कर रहे हैं, इसका 1 plus some squared polynomial बना रहे हैं. ऐसे करने से हमें ये separate करा हुआ दिख रहा है. So what we would say is when we look at certain feature space, we may need a linear kernel. और वी में नीड अ पॉलिनोमियल कर्नल. जैसे कि एग्जांपल पहले देखा, दो वेरिएबल्स हैं, उसको आपने कोई रेस टू 2 किया, हो सकता है रेस टू 3 करेंगे तो क्यूबॉइड लीनियर लाइन बन जाएगी, है ना. इस तरह से यू जस्ट सी हाउ द डेटा इज एंड मे बी यूज अ गॉसियन function or maybe use a sigmoidal function. So you have to use the right function to see to it that the data becomes linearly separable. Looking at the space that is there, you may use a linear kernel, you may use a 2 degree 2 order polynomial, you may use a 4 order polynomial or a nth order polynomial depending upon the kind of data that you are having. So n order kernel you will use, or a linear kernel, or a any type of kernel, or a Gaussian kernel. If the data is not separatable like this, हाँ, ये बीच में पॉइंट्स आ रहे हैं और ये साइड साइड में ये स्क्वायर पॉइंट्स आ रहे हैं, so you may not use a linear kernel, you may go and use a Gaussian kernel, which is able to differentiate the two classes. What we have to say is SVM is only being used wherever there is a two classes. अगर आपके पास एक से ज़्यादा classes हैं, what you do is you take one class, you learn an SVM for that one class and all the rest. Then you take the second class and then work in SVM for the rest, and take the nth class and then work in SVM for the rest. So SVM can only handle two outputs. Okay. Then to predict the output of the new input, just predict with each SVM and find out which one puts the prediction the farthermost into the positive region. So which is giving the best results, you will take that. Okay. So, support vector machines work well in practice. The user must choose a kernel function and its parameters well. They can be expensive in time and space for big data set. The computation of a maximum margin hyperplane depends upon the squares of the numbers of the training cases. We need to store all the support vectors in over here, so it can become quite expensive in time and space. The kernel trick can be used even in PCA, which we have not studied. We'll study it later. In PCA in much higher dimensional space, thus giving a non-linear version to PCA in original space. So this is where it is being used.